busy. So we're gonna go through as much as possible. Then so far we try to build a 3-node model, which is simple, very simple 3-node model, and then we made it happen. Where is it? Yeah. This is what happened. This is what we have. The result can be different always, depending on what values we have. But however, anyway, we have pretty much the same, not really same. It's quite different, right? Let me see what made the difference, because gas generator providing almost everything and the others really doesn't provide anything. I just want to double check what happened to this to these generators. Gas generator one supposed to be P norm 50 and marginal cost of 50, and then gas generator 2 supposed to be P norm 20 and marginal cost 40. We are debugging it. 50, 50, 30, 40. However, it's not too much different. It's not too different. And then we have a bus which is 40 and 30. Let me go back. 40 and 30. It should be fine. I don't know. Can be different. Doesn't mean that we can't go through anyway. So we will go through to the output, and then I will double check what happened to this generator later, and then I will share it with you. Okay. And I think it should be all fine, but probably demand can be different, or maybe the link had slightly different information. Bus 2 and bus 100 and bus 3 and 1 link, they are all correct. Can't figure it out at the moment, but I will figure it out later and then we'll share it. Okay. What we will do as a next step is unit commitment. So basically, the reason that I want to do this PipeSA course is not actually to let you know how to use PipeSA, but to share the idea what power modeling itself is, because these days AI can do this PipeSA modeling quite well. So in many cases, practically you don't need it. However, if you don't know what model you need, then there is no way you can build a model even if you have AI, right? So that's the reason of doing this course, to let you know what kind of power models that we can do. One of the most important thing is unit commitment. So unit commitment means let this model to turn on and off the generator. Why does it so important? Because in real world, when you turn off a gas generator, you can't turn it back on right away, because you need time to cool down and you need time to warm up. You can't just turn it off and then about 30 minutes later, we need electricity, turn it up. You can't do that. So that's what we test using unit commitment. So in case of unit commitment, we have a component, or we have attribute. We use attribute minimum uptime and downtime. Minimum uptime means when this generator is online, or when this generator provide electricity, it needed to provide at least a certain amount of time, like 3 hours or 4 hours or something like that. Otherwise, this generator really cannot make any money, because it takes time to warm up, and during those warm up process, it uses a lot of energy, or it has pretty low efficiency. And then when it hits a certain amount, then it needs to earn money actually by providing electricity, right? That's a minimum uptime and downtime. In case of downtime, it's more like about the cooling hours. And then we have ramp rate. Such as solar in the midnight or coal power plants in multiple functions. Yes, in that cases, same, but in mostly wind and solar doesn't have a minimum up and down time or on and off status, because it can just generate whenever they need. However, in case of coal power plant, when it went to mole function, like when it stopped out of sudden, then it takes lots of time to back online, right? Even if it is planned, still it needs a certain amount of time to back online. And then we have startup cost and then shutdown cost. Like, yeah, when you actually start up, you need to pay more to start up the engine. Like, because its energy efficiency is way lower than generating electricity. Yes, that's correct. So these power generators are not always very flexible. So what we would like to try is I want you to understand the purpose of unit commitment, and I want you to understand how this can be modeled in PIPESA. This unit commitment can be used for generator scheduling, when to fix a generator or when to do operate on like management, maintenance operations do in the summer or in the spring or autumn. When do we need to do it? Or we can we can use this unit commitment to find the most suitable time to do the maintenance job or maintenance task. And in case of South Korea, Jeju Island, as I said before, there is a term called must run. In that case, some generators always must be online to provide a certain flexibility to the system. So that's the other way of using unit commitment. It must be status on rather than off. Right? Also, we can support reliability and reserve planning using unit commitment, and we can also consider thermal flexibility as well and investment insight as well. Because when you do the investment when you invest on a certain generator, let's say gas generator or hydrogen generator, if you need to turn it off for I don't know, maybe 12 hours or 12 hours a day every day, then you need to carefully consider if this market is really profitable to yourself. So that's the place where we can use unit commitment to understand this profitability. There are some attributes that we are going to add in the model. One is PMIN PU. That's the first one is committable. So in PIPESA, when you turn committable true, it means you are letting the PIPESA to decide to turn on or off this generator. Okay, if committable is false, PIPESA assume this generator is always online, which means there is no minimum downtime, right? So if you want to test minimum downtime, you need to set committable true. And then we have Pmin PU. This is exactly opposite of Pmax PU that we used before. In case of Pmin PU, if Pmin PU is 20%, means this generator can provide electricity only after it generates more than 20% of its capacity. So there is a technical reason why there is Pmin PU, is because one is usually generators' electricity is not very stable when they provide small amount of electricity, like say 5% of its capacity. It's not really stable always. So that's why we need some sort of minimum power generator, minimum supply of each generator. And this is very technical features. Is different by generator. I mean, even if the same gas generator, they all have different min PU, right? And then also we're gonna set startup cost and shutdown cost and minimum uptime and downtime and etc. We can set all of them. However, in this example, we are going to set the committable true, and then we are going to set startup cost as a 50% of marginal cost, which is not too high actually, which is pretty low. And then we are going to set minimum uptime as 5 hours, and then minimum downtime as 3 hours of all generators. Okay. we are gonna do that, and then we will see how this result changes. But before we go through, just in case, let me run the entire process just once again. Yep, still, guess one is a bit weird, but it can happen anyway because that's the cheapest one. And then what we are going to have is network dot generators. If we see the generators, this is the output. Right? If we see commutable, guess one's commutable is false, guess two is false, guess bio is false. They are not commutable at all, which means pipes are always assumed this is always on. We are going to change it to true. And then we see it. Now it became all true. Now pipes are will turn it on or off based on its cost optimization process. Right? And then network generators startup cost is going to be network generators marginal cost multiplied by 0.5. So setting the startup cost to be a half of the marginal cost. And then we are going to set minimum uptime and minimum downtime. Network generators mean uptime is 5 hours. Network generators mean downtime is 2 hours. You know, it's very nervous to run this unique commitment because it is quite easy to hit infeasibility. Was it 3? Yeah, doesn't matter. We are just testing it. It's not really important. I'm gonna try 2 because 3 is more strict. Be nervous. Network optimize. And if we run it, yeah, ended up infeasible. Let's try to solve why it ended up infeasible. Let's go through from the beginning again. Let's do the let's do the debug all together. We have a capacity, and then we have proper gas generator, which is 50 megawatt, capital cost of 50, and then gas 2, 30 and 40. And we have bio, which are pretty okay, 3 to 1, since they are all okay. Then what I can assume is probably minimum uptime and downtime are too strict for those. So we can change it, and let's try to run it. Huh. That's a bit weird. Yeah, I think there. Yeah, I just wondering what happened. Let me go back. Sorry about that. I didn't expect this sort of result at all. This didn't happen before. Let me double check it. Your model optimized, and mine is wrong. I'm the one with the problem. Yeah, now I have the. Yeah. I think I put some wrong numbers there. Sorry about that. Yeah. 5 and 2 and optimize it. Now I have optimal result. Yay, finally. And then we will see its output. Pipes are underbar plot network. That's the function that we had. If we compare the result with the previous one, let's just zoom in a little, maybe just a small part. This was the result. And then if we zoom in a little, seems pretty much the same to me. And which means this unique commitment did not affect too much. Let's make sure if that's the true by seeing the generator result. T.P sum. And if we get the output from this committable, where was it? There was an output above somewhere. Interesting. Those two results are pretty much the same. So it actually unique commitment did not affect the entire optimization process at all. But in many cases, actually, what happens is when you have unique commitment, it affects the result quite a lot, and it easily causes the infeasibility, which I experienced a little before. So, but fortunately, we don't have that issue. And let's see each status network generators.t, and we can type status to run it. Those generators, all the generators are pretty much always on, which seems for me a little weird. Then we will debug if things are all correct, right? We go to network generators and then see the committable. Committable is true, and the result is but still it was all online, which means I would assume it's correct result. Network generators are key. So basically what happened is Pipesa decided to turn this entire generators always online to make sure to make sure or to provide enough electricity to the entire grid. That's what happened to this system. That's what unique commitment is. And then now we're gonna go to the economic dispatch, which is slightly different. I mean, almost, yeah, slightly different. Some people find it slightly different, but some people find it totally different. But unique commitment and economic dispatch are quite closely linked. So unique commitment is to let the model to decide turn on or off the machine, right? In case of economic dispatch, to let this machine to choose the most economic mix of each hour. That's what economic dispatch does. So basically, it's cost optimization as we did before. But what's difference is in case of economic dispatch, we use more attribute than before, such as we don't need to go through all those. Economic dispatch is basically for cost minimization. So this is what we've been doing so far. And real-time feasibility, simple and scalable, that's what we've been doing so far, is all fine. But what's different is we add some more attribute, such as ramp limit up. So in case of power generator, like say gas generator, you cannot generate electricity from zero up to 100% in an hour. Usually it doesn't happen. In South Korea, usually that that's called what ramp up rate. In South Korea, ramp up rate is usually less than 10%. And if the ramp up rate is not really high enough, then the entire system can be infeasible. However, if the ramp rate is too high, then because the power generator will have lower efficiency and it will cost more and it will emit more greenhouse gases during the process of ramping up, right? So we are going to test what happens if we set ramp limit up to 0.2, which means limit the maximum power up rate to the 20% of total capacity. So if the generator's capacity is 100 megawatt, then every an hour, generator can add only 20 megawatt for each hour, right? So it takes 5 hours to go to 100% from zero. And we want to set minimum P min PU, which is 0.2, the 20% of the P norm, so that power generator can be on the market, or they can sell the electricity to the grid only when their electric generation is more than 20% of each capacity. Does it make sense? Nobody's here? I'm the only one? Okay, thank you. So what we are going to add is network dot generators ramp limit up equals 0.2. Network generators dot P min PU equals 0.2 as well. And then if we see, if we optimize it, we have feasible result. So far, so good. Anyone with infeasibility? I hope nobody. Let me give you about 30 seconds to follow up, because I think I went too fast, although I made all the mistake and infeasible for myself. If you don't it, let's see the result. Types of plot network. Doo-doo. It's super different, right? It's super and ultra different, right? Compared to the previous, which was pretty much, not this one. Where is it? Where is it? Yep. Which was something like this. Now we have much more flat gas one generator, right? We didn't have gas one generator here, but now we have much more flat gas one generator. And if we zoom in, we can figure what happened. See, gas one generator's capacity is 50 megawatt, and we set the P min PU as 0.2, right? So if this entire system wants to use gas generator one, then it must provide at least 20% of its maximum capacity, which is 10 megawatt. So even though probably gas one was not the cheapest one, still it needs to buy electricity from gas one generator. That's basically what happened. I mean, if there are like 100 megawatt of gas two generator or bio generator, then probably there is no reason to buy electricity from gas one. but because it's not the case here, even though this is not the most cost optimal solution, still because of those restrictions and also called constraint, gas generator 1 becomes a important source to provide electricity. Can you see the difference? Is there a way to summarize the utilization rate of each power plant relative to their PNOM? Yes, of course, you can simply do it using network dot generators dot p dot sum. This is the easiest way. Sorry about that. I missed underscore t. And then we have network dot generators dot p num. Right? You can calculate capacity factor using capacity and each electricity output, which is called capacity factor or utilization rate. Right? The unit of this output is megawatt hour, and this is megawatt. So be careful about the unit, but this is how we do it. And what about we try something like exercise? Let's try to change ramp limit up of gas 1 generator, only the gas 1 to 0.4. And let's see what happens. Okay, change ramp limit up from 0.2 to 0.4 for S1 from 0.2 to 0.4. And let's see what happens. This is what we are going to do. How can I do it? Network dot. This is Python, and I told you that this is basically object, right? If we type network generators, then you can see, oh yeah, okay, here is gas generator, gas 1, and probably can access something like this. Let's try. It doesn't work that way. Then probably we need to add ROC. Yes, it works. Because this is Python data frame, basically, you can access to all the value using this way, right? And then you can also access to ramp limit up. Is it possible? Yes. And what if we change it to 0.4? It says something very long because we used ROC and ROC. Better way is gonna be something like this, right? Now this has a ramp limit up. Where is ramp limit up 0.4? Right? Easy. If we run it, let's see what happens. It takes a little longer time, right? Because of the different ramp limit up, now calculation became a little more complicated to the model. I think this might take too much time. Actually not. Types are plot network. The result is again quite slightly different. We can see much more gas 1 generator jumping in during the first couple of hours or during the first couple of days, right? And then out of a sudden, previously gas 1 generator always provided about each 20% of electricity, right? However, now because gas 1 generator can ramp up much faster, it doesn't need it to. So then now system entirely just turn off the gas 1 generator and then turn it on when it's required, and then still you can follow the demand or its fluctuation. Okay, Charles.
Hi, Sanghyun. Yeah, actually, my question is, isn't the P min PU supposed to be the minimum for the... Oh, because we're running a unit, it's also a unit commitment problem.
Yes,
Okay,
yes.
I see it now. I see it now.
That's
Yeah,
thank
but
you.
in my results, it's not turning gas one off. But I guess that's all right.
Let's see it later. Okay. And that's what we have. So try to change PMIN PU to zero point 0.5, a small exercise on your own, and then let's share what happened. We want to see the cost, right? So we want to see the marginal cost. Let's try to see what happens. Here is the output so that we can just type network buses marginal price. What's the result? It doesn't have the marginal price and marginal cost. I think no. Let me double check it. Buses T marginal price. It's all zero. It's weird, right? It's just zero. There's no marginal price at all. Although we had the marginal cost of electricity, marginal price of each bus is zero. Something's wrong. Why? Because when you want to calculate the marginal price in PIPSA, commutable must be false. That's interesting, right? So what is locational marginal price first? Locational marginal price is electricity, basically electricity price of different location. Right? Those area with more generators usually have lower, I mean, more cheaper electricity generators have lower marginal price, but those area with a much more expensive electricity generators or lack of transmissions usually experience higher marginal price. In case of South Korea, there is a new rule to introduce in South Korea in a couple of months, which will have two different marginal locational marginal price in South Korea. So those area near Seoul will have a higher electricity price compared to the other region, due to transmission limitation. So in pipes, if you want to see the marginal price, because the marginal price is dual variable, I don't want to explain you what dual variables are because it is too much technical. However, what you need to remember is first, to get the value, the model must be feasible. Of course, if the model is not feasible, then there is no way we can get the result at all, right? And then second, it must be solved with LP, linear programming, not mixed integer programming. So what does it mean? LP is linear programming which only uses a continuous number. Mixed integer programming uses continuous number together with binary and something else. So in this case, commutable, when you set commutable true, pipes decide to turn on or off each generator, right? Here, on and off is binary. It's 1 or 0. So it becomes mixed integer programming. So in mixed integer programming, you don't get dual variable in pipes, so you can't get the result. But we still want to get the output from um, unit commitment. How can you do it? So what we need to do is we need to run the model twice, getting more complex, right? We need to run the model twice. First, we need to run the model with the unit commitment, right? And then second, set the committable with the false, and then copy the statures to the model, and then run it again while setting the commitment false. So two different model running is required. let's do it line by line, and it's not too complicated. It seems very complicated because I don't think I delivered explanation pretty well, but in the code, it's much more clear, right? So we already have the result of this unit commitment and economic dispatch, right? So we must be able to have something like general network generators, T status. If we copy paste, you must be able to get the value something like this. Let's see what is the sum. Guess one, out of 480 hours, guess one was online about 448 hours, and guess two was 472 hours. Right? This is status of unit commitment. Let's copy it to where status fixed. Let me copy. And then network generators committable equals false. Then what we needed to do is network generators T status equals status fixed. Doing this way, we're gonna fix the status of unit commitment while we don't, sorry, network generators T status equals status fixed. This way, we wanna fix the status of this network while we are not going to have unit commitment. So still committable is false, but committable is false, which means pipes cannot decide to turn on or off each generator, right? However, because we fixed status from the unit commitment, we can just force the pipes to follow the fixed status. That way we can mix, or we can get the result from unit commitment and then put it into the next optimization process, which is economic analyzation. We are going to optimize it, but very important, perform unit commitment is false, saying do not do the unit commitment. And then we want to run it. We have some output. Now we are going to see the result. Network dot bosses T dot marginal price. Yay, we have some result. It was all zero, but now we have the result. We're gonna see the output in a chart. You can just add dot plot. See? Bus 2 is not here, probably because it is overlapped with something else. But bus 1 has a bit higher price, marginal price, than bus 3. I think this is because of those, mainly because of this, because of electricity loss during the transmission. That's my assumption. So that's what we covered today. Is there any questions so far about this two-way or double optimization? I mean, if you use more complicated model or more commercial model like Plexus, you don't need to worry about this dual optimization. Usually, model just handle it and then give you the result right away. However, Pipesa is a open source and more flexible model, so then you can do whatever you like. However, flexibility means you need to touch things around a little bit more than commercial model, right? So that's what we covered. So based on the result we have, based on the model, we have this result. And then what you can test is you can set different value for each variable. Probably you can set different marginal cost, or you can try to set different efficiency of link or something like that. And then let's discuss about it during the next week session. Okay. Please have a look at this advance while when you have time. I'm pretty sure it will not take more than 30 minutes, so please invest about 30 minutes to recap what you learned today.